In this tutorial, let's think about a constant pressure process on a perfect gas in a closed system. And that perfect gas is initially in this equilibrium state 1 with properties N, T, V, and P. And what I want to do to this gas here in the piston cylinder assembly, the gas is occupying this volume. I want to, for example, heat it, but keep the pressure the same. So if we were to heat the gas and the pressure had to stay constant, then clearly it's expanding and increasing its volume. If we wanted to do an isobaric cooling on this gas, I wanted to cool this gas, the pressure would definitely drop if the volume were the same. So in order to keep the pressure the same, the volume's going to have to drop, right? Okay, and I could specifically point out that I'm doing an isobaric expansion or an isobaric compression. We don't usually describe it that way. We would say instead that it's expanding or being compressed against a constant pressure or external, if you like, pressure. And sometimes we go so far as to say which is equal to P final of the gas. Now, I'm just going to underline this part because it's not necessarily always pointed out in a question, so you don't want to expect that this is written. You'll see it in an assignment. We may not see that on a midterm or exam. But think about it. The gas will reach state 2 and achieve mechanical equilibrium when the pressure inside and out are balanced so that I have a mechanical equilibrium. And so P final of the gas and the P external are going to be the same because this piston has stopped moving. And so we'll typically just see it written like so, against a constant external pressure. Okay? And because it is a constant external pressure, we can think of this as being irreversible, an irreversible process instead of a reversible one. Okay, so the scenarios under which this is going to happen, sorry, I have a really squeaky chair, are just that, if the problem states that this is an irreversible expansion, or if the problem states that this is an expansion or compression against a constant external pressure, that's going to indicate irreversible as well. Another scenario, we have a chemical reaction. There are gas products, and they are the chemical reaction, is being done on the bench at a constant pressure. And so the gases that are formed as products in that reaction would actually be undergoing a constant pressure expansion because they're pushing back 1 atmosphere pressure. That's another example of irreversible. We can also expect to have van der Waals gases, real gases, adhering to van der Waals equations, that have a van der Waals pressure initially, a van der Waals pressure finally, and that is the external pressure against which this process has taken place. And finally, if we hear something like a 1-step or a 2-step expansion or compression, then that, of course, is irreversible as well. Okay, so in these cases, again, this is not an adiabatic change, it's an isobaric one. And so I can make use of the fact that could if this was adiabatic as well. Like in state 1, I have P1V1 is equal to nRT. And I know over here that P2V2 is equal to nRT2. And I can now, I'll point out again that since this is not adiabatic, I can make use of P1V1 over T1, being equal to R, and that's equal to P2V2 over NT2. Now it's closed and is constant. It is a constant pressure process, so these guys are the same. And I'm left with V1 over T1 is equal to V2 over T2. So I can rearrange this to isolate for any one unknown that may be the initial or final volume or the initial or final temperature. Because it's not adiabatic, this little operation holds true. Yeah, so again, I could rearrange this to find any initial property, or rearrange this to find any final property, or make use of the fact that both of these assemblies equal a constant, and isolate for an unknown as a result of the change. Okay, so what about WQ, delta U, delta H we had written up here? A good place to start always, as I say, is the first law. So du is dq plus dw. And then I want to think of the condition on this change, constant pressure. The fact that it's constant pressure is not going to make either one of these go to 0. But let's start with work. Now, dW is equal to a minus PdV. Regardless, that's my starting point, whether or not this is reversible or irreversible. And I know that work then is equal to the integral of minus PdV. So in this case, because it's a constant external pressure, I can pull that pressure out and say that that work is equal to minus P integral dV, and therefore work is a minus P, and sometimes I write external here, but I may not, delta V. Okay, let's pull this over so we have more room to write. Okay, and this P external is the P final of the gas in this irreversible expansion or compression. And the delta V, of course, is equal to V2 minus V1. So if these are not known immediately, then we can rearrange the PV-nRT equation in the second state or in the first state to get these values. So that would be my work. Now, dq. Remember that in general, dq over dt is equal to c. Not a useful formula to plug into, but it is a good expression to start with. And so that tells me that dq is equal to c dt. Now in this case, it is a constant pressure change. So I have dq sub p. Now the heat exchange between the system and the surroundings under a condition of constant pressure is actually equal to the enthalpy. And that's equal to, oh yeah, that's right, Cp dt. And so if I wanted to find a value for Q, I would have to integrate this, which is the integral of this, and so on. Now I'm missing something here because this is really a molar heat capacity or a specific heat capacity. So molar per molar, specific per gram. We use molar, so that's why I'm writing CPM. And that's going to be joule per k mole times K, so I'm going to have joule per mole, but I really need joules, and that's why I need to slip in a number of moles here. So I have that dq sub P is equal to, well, I can take that off now, that's equal to a delta H, and that is equal to n integral Cp molar dt, and if the heat capacity is independent of temperature within my T initial final limits, then that pulls out of the integral sign as well, and I have n Cp molar delta T. So that's a really important formula there. Okay. So we have formula for work, we have formula for Q. When we have both of these, we have a formula then for delta U. That would be, in this case, Q sub P plus the work. I'll just remind you that what is always true for enthalpy, its thermodynamic definition, that H is equal to U plus PV, and therefore a delta H is equal to delta U plus the delta of the PV product. Now, because this is not an adiabatic change, but it is a perfect gas, I can substitute the PV product for nRT. And delta nRT becomes just simply nR delta T, because temperature would be the only thing that's changing. And so just like in the other tutorial where we were doing constant volume, but this one's constant pressure, we see that delta H is equal to delta U plus, now because pressure is constant, that's going to be P delta V. So maybe this is going to serve us, or delta H is equal to delta U plus nR delta T. So maybe this will serve us. Okay? They're both going to be true. It just depends on what sort of information I have to put in here. So again, I just want to, because this is a tutorial, I want to pull that out again and just show you again where that came from. The delta of the PV. Now remember that PV is equal to nRT because this is a perfect gas, and so this is also equal to this. And so that is equal to an N1RT, or I keep doing one, final, minus initial. But N and R are constant, and so that's why that becomes that T2 minus T1, and now you know where the nR delta T comes from. Okay? And similarly, this delta PV could be P2V2 minus P1V1, but this is a constant pressure process, and so that's P2 and then V2 minus V1, or simply P delta V. And that's what I have here. Okay, so I think that covers that for a constant pressure heating or cooling. And we've got the work, that's minus P delta V. We have the Q, which is a Q sub P equal to the enthalpy delta H, and that is equal to n Cp molar delta T, and that's only going to come out of the integral sign if it's not dependent on temperature, and there's a good example in the text where it is and how we integrate that. And the internal energy we could probably get just by rearranging this. So although I've drawn the box around the equation where I've isolated for delta H, and what I probably should have done is isolate for delta U. So delta U is going to be equal to delta H minus P delta V, or delta U is equal to delta H minus nR delta T. All right, good stuff.